Good morning. Today we are going to prove the very important theorem, the next one. Let fz be analytic in a simply connected domain consisting the simple closed contour C. Suppose this is your simply connected domain D and it is containing the simple closed contour C. Then fz has derivative at each point z0 inside C. This is the contour C and derivative of f dash exists at each point inside C, right? Then we have to show that f dash z0 is equal to 1 divided by 2 pi iota the integral of fz divided by z minus z0 whole square dz. To prove this result, we first need to show that f of z0 is equal to 1 divided by 2 pi iota the integral of f of z divided by z minus z0 dz over C. We have already proved this result in the previous content, but here I am again going to prove this in another way by taking the definition of continuity, right? So first we are going to show this result, and from this result we prove this result, right? Okay, let's start. First, the definition of continuity. Since f is continuous on its domain, it is given that fz be analytic in the simply connected domain. Analytic means its derivative exists at all the points, right? So that means f is continuous on its domain and in particular also at this point z0. And then we have taken the point z0 at the center. To apply the definition of continuity, we need to construct the circle C1 inside this closed contour C. Mod of z minus z0, the circle is centered at z0 having the radius r. So therefore, for a given positive epsilon, we are going to apply the definition of continuity now. We have constructed this circle inside C. Construct a circle C1 inside C and small enough so that the mod of f of z minus f of z0 is strictly less than epsilon for all z on C1. For all z on C1. So now if I apply the Cauchy's theorem for multiply connected region, because I need to show this result, for that let's consider this integral. This integral over C will be equal to the integral over C1. By Cauchy's theorem for multiply connected region, the integral over C of the function equal to the integral over C1. So for this integral we are considering the function fz divided by z minus z0. We have to take the integral of this integrand over C and this will be equal to the same integrand over C1. So by Cauchy's theorem for multiply connected region, the integral of fz by z minus z0 over C is equal to the integral of f of z divided by z minus z0 over C1. This is a corollary for the Cauchy's theorem for the multiply connected region. So this can be written as further, let me add and subtract f of z0. And now I am going to separate this. I am taking the integral over first f of z0 divided by z minus z0 dz and taking these two together. Now this is the constant, right? If I take this constant outside of this integral, what is integral of 1 divided by z minus z0 dz? This will be equal to, yes, if I take z minus z0 to be equal to e the power iota theta, dz will be iota e the power iota theta d theta, right? So when you put over here, this becomes 1 divided by e the power iota theta into iota e the power iota theta d theta with limits from 0 to 2 pi, right? So these two cancelled out and we have got this to be iota. When taking the limits, the integration of 1 with respect to theta is theta. So when taking the limits, we get 2 pi iota, right? So the integration for this integral is 2 pi iota. So when taking fz naught outside, the value for this integral is 2 pi iota plus, very fine, okay. Please mark this as 1. And now if I consider this second term, and let's take the mod of this term. So since if I take the mod of the second term, this will be less than equal to the integral over C1, the mod of f of z minus f of z naught divided by the mod of z minus z naught mod of dz. And by the definition of continuity, this mod is strictly less than epsilon. So writing this further as it is strictly less than epsilon divided by what is mod of z minus z naught? It is r. Yes, we have constructed the circle C1 z minus z naught mod to be equal to r. So writing here r for this and taking the integration over C1 for mod of dz. This is nothing but the circumference of the circle C1. So that is 2 pi r. So r cancelled out and we get here 2 pi epsilon. This mod to be less than, strictly less than 2 pi epsilon. But epsilon was arbitrary. We can choose epsilon as small as possible, 0.000 so on, right? 0.0001. We can choose epsilon to be very too small, a positive real number, but epsilon was arbitrary. So therefore the absolute value of this will be equal to 0, and let's mark this as 2. So what is 1? We have marked 1 to be the integration of fz divided by z minus z naught is equal to this right hand side, and from 2 we get this term to be equal to 0, right? So from 1 and 2 can I write is equal to 2 pi iota f of z naught, other term is 0 from 2, right? So it is this only. If I take this 2 pi iota to the denominator of this left hand side, we get 1 divided by 2 pi iota of this integral to be equal to f of z naught, which is nothing but our Cauchy's integral formula. The first Cauchy's integral formula, right? Which we have already proved in the previous content. And this is another way to prove this result by using the definition of continuity. And now we have to prove the required result for f dash z naught. Let's choose h small enough in absolute value such that mod of h is less than equal to r by 2. If C1 is a circle centered at z naught having the radius r, this h we have taken, the mod of h is less than equal to half of this distance, the radius. So therefore, if I add the point z naught to h, that will be inside C, it will remain inside C. H is less than equal to r by 2. H is less than equal to r by 2. And if I add the point z naught to this h, then this sum will remain inside this contour C. Yes? So if I mark this previous formula to be as 3, so from 3, if I replace this z naught with z naught plus h, so from 3, let's replace z naught with z naught plus h. Now because we know that limit h tends to 0, f of z naught plus h minus f of z naught divided by h is equal to f dash z naught. So that is why I have considered the mod of the difference of these two, because we need to show that the result f dash z naught to be equal to 1 divided by 2 pi iota the integral of f of z divided by z minus z naught square dz. This we need to show, right? This we have to show. So to show this result, I am going to replace f dash z naught with this right hand side in this mod. And then later on, I will show that this mod is equal to 0 so that we can get our desired result. So let's replace f dash z naught with this right hand side in the mod and require to prove that this mod is equal to 0. So for this, I am going to use this result. Let me mark this as star. So from star, we are using 1 divided by 2 pi iota the integral of f of z divided by z minus z naught plus h dz minus, for f of z naught we write 1 divided by 2 pi iota the integral over c f of z divided by z minus z naught dz, and this complete is divided by this h, minus 1 divided by 2 pi iota the integral over c f of z divided by z minus z naught whole square dz, and then having its mod. So this is equal to, let's take 1 divided by 2 pi iota common from these two terms. So the integration of, I'm writing here z minus z naught minus h minus 1 divided by z minus z naught, and writing here f of z dz, also divided by h, then minus second term 1 divided by 2 pi iota the integral of f of z divided by z minus z naught whole square dz, and then having its mod. When taking the LCM of this, what we get? We get z minus z naught minus z plus z naught plus h divided by z minus z naught minus h into z minus z naught. So z naught is cancelled out and z is also cancelled out. We have h in the numerator, and that h is now cancelled out with this h, right? So what we have inside the bracket? 1 divided by the product of these two. Let's merge these two integrals together. Again, when taking the LCM of this, h into z minus z naught, and in the denominator just multiply this with z minus z naught whole square. We have adjusted the numerator and denominator, and then f of z dz mod, right? So these two cancelled out from here, and taking this h outside the integral. Now by Cauchy's theorem for multiply connected region, we know that integral over the curve C is equal to the integral of the same integrand over the curve C1. Reason we have used by Cauchy's theorem for multiply connected region, right? Now this mod is further less than equal to the mod of h divided by 2 pi iota the integral over C1, it is f of z divided by, taking the mod of f of z divided by the mod of z minus z naught whole square and the mod of z minus z naught minus h and the mod of dz. Now as this function fz, it is continuous on the circle C1, and also it is bounded on C1. It is bounded on C1. Why it is continuous and bounded? Because it is given that fz is analytic on C, inside C, inside the closed contour C, and this C1 circle is constructed inside this closed contour C. This circle C1 is constructed inside the closed contour C, right? And it is having the radius r. Because it is analytic inside C, analytic which means its derivative exists at all the points of the C, inside C. Its derivative exists at everywhere inside C. So that is why it is also bounded on C1. And because it is bounded on C1, we can have the mod of fz to be less than equal to, let's say, some positive real number m. Right? And now let's use this result over here. So further, this is less than equal to mod of h divided by, what is mod of iota? It is 1. So it is 2 pi, that's it. The integral over C1, mod, instead of mod of fz we write capital M for this inequality, divided by, okay, because this is a circle C1 having the radius r, so mod of z minus z0 is r. Because I am having the square, so I am writing here r square for this. Sorry, it is multiplied. These two are multiplied together. So writing here r square multiplied with z minus z0 minus h and mod of dz. Very fine. Is it okay over here? Alright. Let's take this m outside of this integral. And also we can take r square outside this integral. So furthermore, I am having mod of h capital M divided by 2 pi r square and the integral of this integrand. This integrand is less than equal to 1 divided by mod of z minus z0 minus mod of h, using the result, and mod of dz. Why I have done this? So that again I can apply mod of z minus z0 to be equal to r over here. So if z minus z0 is equal to r, and we also know that we have chosen h to be small enough such that its mod is less than equal to r divided by 2. Can I write the reciprocal of this? So further we write this to be less than equal to mod h capital M less than equal to, for this sign, divided by 2 pi r square, the integral of C1. So it is 1 divided by r minus r by 2, mod of dz, and r minus r by 2 is r by 2, or we write it as 2 divided by r. So these two cancelled out with this. So this is further equal to mod h capital M divided by pi r cube and the integral of mod of dz. And the integral of mod of dz is nothing but the circumference of the circle C1, that is 2 pi r. So writing this further as mod h into capital M divided by pi r cube into 2 pi r. So this r is cancelled out with this. We have here r square, pi is cancelled out with this. We have mod of h 2m divided by r square. We have considered this mod to be on the left hand side, which is less than equal to mod h into 2m divided by r square. And when letting h tending to 0 in, let's say, let me mark this as 4, in 4, right? Then what we get limit over here h tending to 0, yes, and this will tends to 0. So we have the limit h tending to 0 on this mod, which is less than equal to 0, because the absolute value is always positive, right? So this limit cannot be negative. So we take this limit to be equal to 0. So limit h tending to 0 on this mode is equal to 0. And when the limit of the absolute value is equal to 0 implies that whatever present in this mode, the limit on that is equal to 0. So limit on this complete bracket is equal to 0. Can I take this second term to the other side? So what does this left hand side to be equal to this right hand side means? It means that the function fz is differentiable at z0. So thus fz is differentiable at z0. For the left hand side I am writing it is nothing but f dash z0 to be equal to 1 divided by 2 pi iota, the complete right hand side. Now but this z0 is arbitrary. Z0 is arbitrary. So therefore the function fz has derivative at each point z0 inside C with f dash z0 to be equal to 1 divided by 2 pi iota the integral over C f of z divided by z minus z0 whole square dz. So here ends up our proof for this result. Alright, thank you, stay blessed.